This diagram maps the standard home-routed roaming topology. When a subscriber uses data abroad, their traffic is encapsulated and forced into a geographic trombone, routing from the visited network across an ocean to their home country's gateway before breaking out to the internet. For modern, latency-sensitive applications like video calls and cloud services, this intercontinental detour visibly degrades performance. The round trip frequently adds 300 milliseconds or more of strict geographic latency to the data path. Here, the 3GPP standard alternative, local breakout, shows the packet egressing directly to the internet from the visited network. By eliminating the transoceanic routing entirely, latency drops from hundreds of milliseconds to tens. However, choosing local breakout forces the home operator to cede the session anchor. Subscriber IP allocation, deep packet inspection, and real-time charging are all handed over to the visited roaming partner, requiring complex bilateral configuration to execute properly. Legacy standards present a rigid binary. Operators must choose between delivering unworkable geographic latency to their users or surrendering commercial and technical authority over the session. Regional breakout circumvents this limitation entirely. It acts strictly as a geographic deployment topology, assembling standard 3GPP network functions in a novel configuration. Instead of routing data back to the home country, the operator anchors to user plane by projecting a working copy of its own internet gateway into a public cloud edge located physically near the visited network. The cloud edge functions like a digital embassy. It is sovereign telecom territory operating on foreign infrastructure. Visitors are served locally and quickly, but the rulebook, identity, policy, and charging remains entirely anchored to the home capital. This hybrid architecture achieves the sub-50 millisecond latency of local breakout while retaining the strict centralized authority of a home-routed topology. Looking at this structural block diagram, we start with the visited PLMN. This domain provides the radio access network and mobility control. Crucially, the visited operator requires absolutely zero modification to hand the session off to the home network. Next is the Google Cloud Platform Edge domain, located physically near the visitor. This cloud tenant hosts the home operator's session management function and user plane function, acting as the decision maker and local internet breakout point for the session. Finally, the home core domain remains physically on premises in the home country. This houses the unified data management and charging functions, retaining absolute control over subscriber identity and real-time billing. These three domains are bridged by specific transport links. The global IPX backbone connects the visited network to the cloud edge, while a private cloud interconnect links the cloud edge securely back to the on-premises home core. Physically distributing these standard components separates where the bytes are routed from who controls the rules, decoupling the localized user experience from centralized operational sovereignty. Integrating these distributed domains requires routing across the IP exchange, or IPX. For 5G standalone networks, the IPX utilizes a Security Edge Protection Proxy, the SEP, acting as the mandatory border checkpoint for inter-operator signaling. In this map, the dashed line represents authentication signaling. When a user registers, the visited AMF routes its query directly through the SEP, ensuring strict security and topology hiding between the two operators. Now look at the thick line representing the user plane payload. This GTP data tunnel bypasses the SEP checkpoint entirely, writing the private IPX transit fabric straight to the cloud edge. The signaling border is deliberately excluded from the data fast path. Forcing high-volume user traffic through a proxy designed for message inspection would create immediate network bottlenecks and reintroduce latency. Meanwhile, policy and charging signaling run on a third path. They bypass the IPX entirely, moving over the private cloud interconnect between the GCP edge and the home core, because they never cross an operator boundary. This targeted routing logic isolates the traffic. It applies rigorous security scrutiny to inter-operator handshakes while keeping the high-volume data and monetization paths completely frictionless. Because regional breakout is an emulated home-routed topology, the visited network processes the session exactly as it always has. The home operator exercises the geographic optimization entirely through its own steering logic. In 4G LTE, this steering relies on geo-aware authoritative DNS at the IPX level, returning the address of the regional cloud gateway rather than a home country node. This call flow trace illustrates the 5G standalone steering mechanism. It isolates the discovery loop between the visited AMF and the Home Network Repository Function, the HNRF, over the N27 interface. During this discovery loop, the HNRF reads the visited PLMN ID embedded in the query. Based on that location, it dynamically selects and returns the specific profile of the regional GCP edge to the visited network. The steering authority is executed entirely by logical nodes the home operator directly controls. This successfully forces the visited network to route data to the cloud edge without requiring a single custom bilateral roaming agreement. Merging standard 3GPP interfaces with public cloud infrastructure creates a profound networking conflict. The GSMA IPX demands static, highly regulated IP routing, while Google Kubernetes Engine relies on fluid, ephemeral scaling. Exposing these rapidly shifting ephemeral cloud pods directly to the global IPX network creates a critical architectural trap. Telecom network equipment is notorious for caching DNS responses far longer than specified. If a cloud worker node crashes and Kubernetes instantly spins up a new pod with a new internal IP, the visited network router will continue transmitting data to the dead cached IP, resulting in a silent traffic black hole. This DNS query sequence shows the necessary engineering solution. The visited network's query must terminate at a static internal load balancer. This abstracts the ephemeral pods behind a stable front door. To ensure the IPX can actually route to this load balancer, the assigned IP must be drawn from GSMA IR.40 registered private IP space, expressly avoiding standard public internet addresses. Deploying cloud-native roaming at scale is only viable when the intense dynamism of hyperscaler computing is securely hidden behind rigid, telco-grade static routing architectures. Beyond the network engineering, lawful interception compliance remains the ultimate launch gate and primary barrier for deploying a regional edge. The legal framework is governed by a simple rule. The physical location of the network function dictates which government has regulatory jurisdiction over the data passing through it. Standard home-routed roaming limits the host nation to transit feasibility. But by moving the session anchor and the internet breakout point onto foreign soil, regional breakout grants to host nation complete regulatory authority over that session. This architecture highlights the jurisdictional split. Operating network functions abroad legally obligates delivering full communication content and session metadata over X2 and X3 interfaces to the host nation's law enforcement. To execute this, virtualized mediation functions, MDF2 and MDF3, must be deployed inside the public cloud. This alone introduces a complex security mandate. These mediation functions must be heavily blinded, ensuring the public cloud provider's infrastructure tooling can never see or infer the existence of an active warrant. Engineering the digital data path is straightforward. Operating it requires navigating localized, sovereign telecommunications law for every single cloud region utilized. Regional Breakout utilizes purely standard BREGPP components to execute a geographic hack on the global roaming architecture. By treating geography as a variable rather than a fixed constraint, operators deliver the low-latency performance of localized routing while maintaining absolute centralized commercial control over the session. Executing this requires a high engineering threshold. It demands bridging IPX rigidity with ephemeral cloud scale while satisfying international compliance laws. By resolving the conflict between performance and control, Regional Breakout secures the future of premium global roaming, mastering the precise intersection of telecom legacy and cloud innovation.